Okay, so just to review a little bit of what we've done with our dosage calculations so far. The dilutions, which is kind of where we started out. Remember, the big thing with the dilution is the dilution is just a ratio. Bless you. And what it is, of course, a ratio of the amount of our concentrate or our medication to our total volume. So the tricky part about dilution was keeping track of what each of the numbers stood for and adjusting them if we needed something different. For example, let's say that we need a 1 in 7 dilution. And we're just going to use the generic terms of serum and water. How much water should be mixed with 25 milliliters of serum? So when we're working with a dilution, the first thing I always do is I write down the ratio of the dilution. This is a 1 in 7 dilution, so it's a 1 to 7 ratio. And then I label what those numbers mean. What does the 1 stand for? 1 is the parts of serum. And the 7 stands for total parts. Well, looking at our problem, we do know the parts of serum. We know there's 25 milliliters of serum. Are we looking for the total parts? Well, not really, not directly. We could find the total parts and use that to get to where we wanted. But what we really want is just the parts of water. So to get to that, one way to do it is to adjust the ratio. Instead of serum to total, we would rather have serum to water. Well, we still have just 1 part serum, but how many parts water do we have? 6. Perfect. 7 total parts. If 1 is serum, the other 6 is water. So that allowed us to complete our ratio, putting the 25 milliliters in for the serum, and cross multiply and divide. 6 times 25 divided by 1 is 150 milliliters. Well, we also use those dilutions to adjust the concentration of a solution. Let's say that we have a 48% solution and need a 6% solution. And the question was, how much water and how much of the 48% to use to create 240 milliliters of the 6%. This doesn't look like it, but this is, again, just a dilution problem. First, we have the desired concentration, or the desired percent, compared to the, sometimes put it the new percent, to the old percent, the old concentration. So in this case, that would be 6% to 48%, which will reduce to a 1 in 8 dilution. Now again, in that dilution, the one there represents the serum or the concentrate. That's the 48%. The 8 represents the total. Well, in this case, we have the total of 240 milliliters. And one of the things we're looking for is how much of the 48% solution. So 1 times 240 divided by 8 is 30 milliliters. So we need 30 milliliters of that 48%. Then, of course, we adjust this. Our total parts would still be 8, but if we're looking for the parts of water, that'd be 7 out of it. If 1 out of the 8 parts is the concentrated, or the 48%. The other 7 out of 8 is just water out of 240 milliliters. Cross multiply and divide, that is 210 milliliters of water. So that's telling us you're going to mix 30 milliliters of the 48% solution with 210 milliliters of water. Now, if you recall, we found a simpler way of doing this, a shortcut for doing this. We need 240 milliliters of 6%. So volume times concentration equals, we don't know how much we need, but we know that we have 48%. So it's volume times the concentration of 48. And now to solve for this volume, now again, it doesn't, I put V1 and C1 as the 6% solution. I could have switched the order. It doesn't make much difference. But what we're going to do here is we're going to multiply 240 times 6, which is going to give us what? 1,440, right? Then we're going to solve over here to get V by itself. We are going to divide by 48 to get 30. So the volume of the 48% solution is 30 milliliters. So that little formula makes it a little easier. It does the dilution and everything for us, right, in the formula. But we still, that is, of course, the amount of 48%. We still need to know the volume of water. How do we find that? Well, if we have 240 milliliters of the 6%, only 30 milliliters of the 48%, the difference has to be made up by the water. Well, then kind of where we left off last week then was beginning the dosage calculation. And I presented you with 3 different ways of doing the dosage calculations. Oops, sorry. So much for no cell phones in class. Huh? Anyways, I presented you with 3 different ways of doing the dosage calculation. So let's say that we have a bottle that says constitute to 120 milligrams per milliliter with 4.5 milliliters sterile water. Let's see, our doctor orders 300 milligrams to be administered. So we need to figure out how much to, and this is of course for injection. How much are we going to fill the syringe and how much are we going to inject into the patient? All right, well, first of all, let's figure out this label up here. There's extra information there. What we need as far as figuring out the dosage is simply the 120 milligrams per milliliter. That is our on-hand dose in our vehicle right there, if we're looking at the formula. With 4.5 milliliters of sterile water, what that is saying is that this vial is generally a concentrate or a powder, and you would inject the 4.5 milliliters of sterile water into the vial and shake it to mix it before you would use it. We don't really, not really concerned about that as far as our dosage calculation. We just care about the 120 milligrams per milliliter. So the 3 ways that we chose to do our dosage calculations. The first way, and I think the least desirable way, is the formula. Remember, our formula was the doctor's orders over the on-hand dose times the vehicle equals the amount to administer. The key to this, of course, is that the doctor's orders and the on-hand dose have to be in the same units. So the orders, pretty simple, 300 milligrams. Our on-hand dose comes from the bottle, the 120 milligrams. And the tricky part for me has always been the vehicle. The vehicle is what carries the on-hand dose, what holds the 120 milligrams and carries it into the patient. Well, it's a little tricky to pick out, but if you look at this closely, it is what carries 120 milligrams is 1 milliliter. So the key is that these units have to divide out. They must be the same. 300 divided by 120 is 2.5 times 1 milliliter gives us 2.5 milliliters to administer to the patient. So on a simple dosage problem like this, the dosage formula, if you remember it and you can get it set up right, it is kind of quick and simple. But again, I don't care for it because once we get into intravenous or IV flow rates today, it's just not so neat and easy. Well, the second way we looked at it was a proportion. And for the proportion, we use the on-hand dose in the vehicle, and then we use that to convert to the doctor's orders. So what we have is the 120 milligrams per 1 milliliter. And we're going to use that to convert. Well, what other information do we have? Well, we have 300 milligrams is ordered. We know that has to go on top because in a proportion, the units have to match up. Milligrams have to be lined up with milligrams. So then down here, we know this will be milliliters. We can cross, multiply, and divide. 1 times 300 divided by 120 is 2.5. So we know we're going to get 2.5 milliliters. So it's nice that we got the same answer both times, at least so far. The last way is what the book calls dimensional analysis, sometimes just called unit conversions or measurement conversions. And I think it's really the simplest way of doing it because you can do any dosage problem using dimensional analysis. And you really don't need to know a lot about what's going on. You always start out with the doctor's order. So the doctor's order here was 300 milligrams. Now, if it is a rate like an IV, it would be a flow rate, like so many milligrams per hour or so many milligrams over 8 hours or whatever. It would be a fraction already because you'd have that unit of time that went with it. Here, it's just a flat-out single dose, so to turn it into a fraction, we have to put it over 1. And we have to now use the information on the bottle to convert that to a usable dosage. The bottle told us 120 milligrams per milliliter. So we're going to use that. We have milligrams here, so to get rid of milligrams with our dimensional analysis, milligrams will have to go down here. Because when you multiply fractions, you can cross-cancel. So 120 milligrams per milliliter means 120 milligrams and 1 milliliter are equivalent. So 1 milliliter will go on top. And now we can multiply. 300 times 1 milliliter is 300 milliliters. 1 times 120 is 120. That divides out to be 2.5 milliliters. Does anybody out there have any major preference for which method we use? Is there anybody that's horribly attached to the formula? Anybody really attached to proportions? You like the proportions? Okay. The proportions are really nice on the simple problems like this because you just set up what's on the bottle and cross multiply and divide.
So I guess if you get more units and problems,
yeah, once you get into the longer problems like what we're going to hit next, intravenous flow rates, the dimensional analysis of unit conversions works a lot nicer. Let me show you what I mean by that. Not even without getting into the intravenous flow rates at this point. Let's talk about this. Let's say that we have a doctor's order of 2,000 units of penicillin. 200,000, sorry. Little hamster hasn't quite got on the wheel yet for the day. There's no O in penicillin either. No extra charge for the extra O. Let's say the label. How do I put this? Label is 100,000 units in 1 gram. 250 milligrams per 2 milliliters. So when we're looking at a problem like this, trying to figure out just how much to administer to the patient, we have our order, which is 200,000 units. U used to be an acceptable abbreviation for units, by the way, so you'll see me use it. Now in the nursing program, they've gone to making you write out units pretty much every time you use it. So we're going to make it a fraction by putting it over 1. So we're going to put units on bottom. What do we have that, this is the units here. What do we have that equates units to anything else? Yeah, 100,000 units in 1 gram. So units would be gone, and we would now be in grams. Problem is we don't really want to be in grams. In fact, grams are not really good for us because we don't have any equivalency from grams to anything else, but we have milligrams to milliliters. So 1 gram is 1,000 milligrams. So the grams are gone, and we're in milligrams. One more move. What's that? 250 milligrams, perfect, to 2 milliliters. Again, the milligrams have to go on bottom, so they'll cross cancel. Now the only units left on here are the milliliters. So now we just have to multiply everything out and divide it out. So we've got 200,000 times 1 times 1,000 times 2, which gives us 400 million milliliters, over 1 times 100,000 times 1 times 250 is 25 million. So if we were to divide that out, this is, I believe, 16 milliliters. So what gets administered to the patient, there is 16 milliliters of that amount. Now, if you were to use the dosage calculation or the proportion, there would be 4 separate proportions here. There would be one proportion to convert this into grams. Once you're in grams, then you'd use another proportion to convert from grams to milligrams, or you could just move the decimal point. Then you'd have to use the milligrams to milliliters. So at least 2 or 3 different proportions to make that conversion. Now I realize having the big long chain out here for dimensional analysis may not be the simplest looking thing either. But I see some looks out there. Anybody totally lost on what I just did? No? Okay. Where this really comes into play is once we start hitting IV flow rates. Most often, IV flow rates are given as an amount to be administered over a certain number of hours. But when you go to actually administer it, depending on whether you're using an infuser or if you're using a manual setup, you either want it in milliliters per minute or drops per minute. GTT is the abbreviation for drops, if you were not familiar with that yet. So the first step is to get it to one of those 2 forms. Generally, we get it to milliliters per minute, and then there's a drop factor that allows us to convert it to drops per minute if we need to. So let's take a look. Let's say that we have an order for 2,000 milliliters of fluid over 8 hours. Now, a couple of different ways that this might be asked. You might be asked milliliters per hour. If we were to ask milliliters per hour, this is a pretty simple problem. Because right now it's 2,000 milliliters over 8 hours. How do we convert that into milliliters per hour? Just divide by 8. 250 milliliters in 1 hour. Now I did it as dividing, remember we talked about ratios and rates. converting to a unit rate, you're just going to divide by whatever the denominator is. I did it that way, but you wouldn't have to. You could literally just divide that out, 2,000 divided by 8, and you're going to be fine. If they wanted to know then milliliters per minute, again, you could use a proportion. You could have used a proportion here, by the way, just having the 1 hour and stuff there, and cross multiply and divide. Milliliters per minute, we already have it as 250 milliliters per 1 hour. We can do a conversion now of hours and minutes. 1 hour is 60 minutes, which is going to give us, this hours cross cancel, it's going to give us 250 milliliters per 60 minutes. If you divide that out, that's going to be 4.167 milliliters per minute. It's a decimal point, not a comma. If we wanted this in drops per minute, we would need more information. We would need a drop factor. So, for example, let's say we have a drop factor of 12 drops per milliliter. Most of the time, your drop factor is anywhere from 8 drops per milliliter up to about 25 drops per milliliter. It depends on the viscosity of the liquid. A thicker liquid, a more viscous liquid, will have larger drops, so it's fewer drops per milliliter generally. So anyway, to get the drops per minute, you would take your 4.167 milliliters per minute per 1 minute, and you're going to get rid of the milliliters. Well, milliliters will go on bottom, so they'll cancel out. Drops are on top. 12 drops per 1 milliliter. The milliliters cancel. 4.167 times 12 is 50 drops per 1 minute. Or 50 drops per minute. Now when you multiply that out, you might end up with like 50.12 or something like that. That's because we rounded off that 4.167. It's really 4.1666666. In my head, I didn't round it off, so it came out to exactly 50. Now, realistically, if we knew from the beginning of the problem that we wanted drops per minute, we wouldn't have done it step by step like that. If we knew from the very beginning we wanted it in drops per minute, I would have done 2,000 milliliters over 8 hours. One hour is 60 minutes. Milliliters and drops. Those are 12 right there. And I would have just multiplied that out and divided. So we would have had 2,000 milliliters. Of course, the milliliters cancel, the hours cancel. We're left with drops per minute. 2,000 times 1 times 12 would be 24,000. Drops. 8 times 60 times 1 would be 480 minutes. Then you just divide that out to get 50 drops per minute. Any questions? So let's say that we have an order for 3,000 milliliters to be administered over 1.5 hours. Let's find drops per minute. If our drop factor is 20 drops per milliliter. So again, we're going to start out with the doctor's order. 3,000 milliliters over 1.5 hours. Now, I converted the hours first last time because for me it's natural. The natural progression is to go from milliliters per hour to milliliters per minute. Because in many cases, if you're using an infuser, a programmable infuser, milliliters per minute is what you want, because that's what you're going to put in the infuser, and the infuser will figure out everything else. So it's natural for me to change the hours to minutes first. It doesn't matter, however. You could change the milliliters to drops first. The only reason I don't do that is there's never an instance where you want drops per hour. Okay? So I'm going to go ahead and just keep doing changing the hours to minutes first. So the hours will go on top, minutes on bottom. 1 hour is 60 minutes. And then I will go ahead and convert my milliliters to drops. 1 milliliter is 20 drops in this case, 20 drops per milliliter. So now let's double check. Hours cancel out, milliliters cancel out, and I am left with drops per minute. So we have 3,000 times 1 times 20 is 60,000 drops. 1.5 times 60 minutes times 1 is 90 minutes. If we divide that out, what are we going to get? Doesn't come out well, does it? 667 drops per minute. Now also, for this class, we will always round to the nearest drop. So instead of 666.66, we will go 667. Obviously, my example is not really good there. 3,000 milliliters per hour is pretty high. Getting over 100 drops per minute is getting pretty heavy dose. If you're in the nursing program, there will be cases where they'll tell you go to 1/10 of a drop or round to the whole drop. If it is a manual infuser, a manual setup infuser, again, it's always rounded to the nearest whole drop. If it's a electronic programmable infuser that takes drops per minute as an input, you would keep it as 1/10 of a drop, down to 1/10. But for this class, we're always going to round to the nearest drop. So let's look at another one. Let's say the doctor orders 400,000 units over 8 hours. Looking up the label and the information for the medication. 100,000 units in 1 gram. For the concentration of 250 milligrams per 200 milliliters. A drop factor. Actually, this should be 250 milligrams per 20 milliliters. Sorry. Take off the drop factor of 12 drops per milliliter. There's a lot of information here. If we were using the dosage calculation formula, we'd be picking away at this for a while. But again, the dimensional analysis, this will all work out on its own. We start out with the doctor's orders, which is 400,000 units over 8 hours. Now again, it doesn't have to be in this order. By the way, we are looking for drops per minute, just so you know. Okay, it doesn't have to be in this order, but it's always my first step to get from hours into minutes, because that's usually what's more interesting, is per minute than hours. So we have 1 hour is 60 minutes is our next conversion. Then we have, what's that? No, that should be 12 drops per milliliter. We're going to be looking for drops per minute. Yeah. So now our next step, we have now, this is going to be in units per minute. So we're going to have to get rid of units. What do we have that equates units to anything else? 100,000 units per gram. For 1 gram. Now, if you wanted to shorten up this conversion, whenever you see 1 gram, instead of doing the process of converting from grams to milligrams, how many milligrams are in a gram? 1,000. So I personally, rather than converting that to putting in 1 gram there, I would put in 1,000 milligrams. Otherwise, in the next step, you're just going to put 1,000 milligrams to 1 gram anyway. Something like that that's a really easy conversion, I make it in my head and just put it in there, save myself a step in the calculation. So now the units are gone, and we're in either grams or milligrams. We're going to say we're in milligrams because the next step would be just to convert the grams to the milligrams anyway. But now we need to get rid of those milligrams. And we have, perfect, 250 milligrams to 20 milliliters. Now our milligrams are gone, we're in milliliters, and of course the last step will be to take those into drops. We have 12 drops per 1 milliliter. So the milliliters will be gone. So now what we're looking at here is we have 400,000 times 1 times 1,000 times 20 times 12. Now we can run into, I'm kind of hoping my calculator does it here. Yes, it did. We can run into scientific notation. You can see there it gives me 9.6 times, or 9.6 e to the E10. What does that mean? Yeah, that means 9.6 times 10 to the 10th power. So that would be moving this decimal point over 10 spots. So we need 9 zeros there. To avoid the scientific notation, we can use our zeros. I usually cross off my zeros in sets of 3 if I can. Like here, there's 3 zeros. Here, there's 3 zeros. There's another 2 zeros here. I'm going to cross those off and those 2 off. I can cross off a 0 here and here. So now when I do my calculation, rather than having to mess around with scientific notation, I'm just going to do 4 times 1 times 1,000 times 2 times 12. 4896, that's going to give us 96,000 drops. And on bottom now, it's going to be 8 times 60 times 1 times 25. So that's going to give us what? 12,000, I believe. So yes, it gives us 8 drops per minute. So cross-canceling is still allowed here with the numbers too, not just the units. Just be very careful with it. You know, you can see I was very meticulous trying to take sets of 3 because I know I can cross those off without making too many mistakes. Just be careful with it is all. And zeros is about the only thing I recommend cross-canceling, because if you start, you're doing, okay, 4 and 60, well, I can make that a 1 and a 15. Too many mistakes get made there. Dosage calculation is one of the spots where mistakes can't be made. So anyway, let's do a couple more examples, and then we'll start talking about dosages based on weight and body surface area. Let's see. Let's say that you are... Let's say that you check an IV that was started before you came on. And that IV is running at 10 drops per minute. The chart says that the IV started at 2 p.m. and is to finish at 8 p.m. How much total is infused? will be infused, I should say. Well, of course, 2 p.m. to 8 p.m. is how many hours? 6 hours. Good. So looking at this, we're working totally backwards now. We don't have doctor's orders. We need to get from what's being administered, or what the flow rate is, back to what the total was, what the doctor's orders were. Okay. So we have 10 drops per 1 minute. We need to somehow get that back to 6 hours, to hours. So we're going to get from minutes back to hours. 1 hour is 60 minutes. And we need to get from drops back into milliliters. So I forgot to put it up here. We do need a drop factor. So looking up for that fluid, the drop factor is 15 drops per milliliter. But the thing is, when we put in our drop factor here, drops are going to go on bottom because they're on top here, and to make them cancel out, they have to go on bottom. So it's 15 drops per 1 milliliter. So now the drops have canceled, the minutes have canceled. Let's multiply this out and see what we have. 10 times 60 times 1 is 600 milliliters. Over 1 times 1 times 15 is 15 hours. That'll divide out to be 40 milliliters per hour. From there, 40 milliliters per 1 hour, we were asking how much over 6 hours. This is one spot where we have no choice but to go back to a proportion. Up here we were changing the units at every step. If we ever hit a spot where we don't want to change the units, we just want to change the numbers, we have to use a proportion. Notice we want to know how many milliliters in 6 hours. We don't want to change any of the units. We still want, milliliters in both, and we still want hours in both. We just want to change the number of hours. So in that case, the only way to just change the numbers without changing the units is to use a proportion. So now, since it is a proportion, we're going to cross multiply and divide. 40 times 6 is 240. Divided by 1 keeps us at 240. So there will be 240 milliliters infused over 6 hours. So let's say we have a flow rate of 40 drops per minute on a fluid with a drop factor of 10 drops per milliliter. We want to know how long will it take to infuse 1,200 milliliters. This is going to be the same type of thing now. We're going to go through our unit conversions or our dimensional analysis until we get to a point. Then at a certain point, we're probably going to have to do a proportion. So we're going to start out, again, working totally backwards. We're going to start out with what's actually being administered to the patient. 400 drops per minute, per 1 minute. So we're going to get rid of the drops. 10 drops per 1 milliliter, so the drops are gone. Let's see where we're at. We have 40 milliliters in 1 times 10 is 10 minutes. Getting pretty promising. We already have now milliliters compared to a unit of time, milliliters per minute. In fact, if I wanted to divide that out, 40 divided by 10 would give me 4 milliliters in 1 minute. We need to get up to 1,200 milliliters. So now I could either I can do one of two things. I can convert this to hours, milliliters per hour, because 4 milliliters per minute is an awful small amount. Or I can go ahead and use a proportion to figure out how many minutes it's going to take to get to 1200 milliliters. Either one would be okay at this point. I'm going to go ahead and do that first, figure out how many minutes. So 4 milliliters per 1 minute is going to take how long to get 1200 milliliters into my patient. So 1 times 1200 divided by 4 is 300 minutes. The reason I did that first is now we are in a unit of time. The 300 minutes is all we really care about out of that proportion anymore. That's how long it's going to take. That would be a legitimate answer. Only 300 minutes is kind of a clumsy unit, so just for the sake of convenience, let's convert it into hours. And yes, it will convert out to be 5 hours. So probably the tougher calculations with these are the ones where we're going backwards, where you actually have the setup there and you see how much is being administered to the patient, and you have to work backwards to figure out what was the order or how long is it going to take or whatever. So let's do one more example here before we hit our break. So you look at a chart. Let's say the chart states, come on. Chart states that an 8,000 milliliter IV was started at 1 p.m. Medication has a drop factor of 12 drops per milliliter. The flow rate set currently is 60 drops per minute. You check at let's say you check at I don't know, we're just going to leave it there. Put it right there. Let's just know when will it finish. Make it simple on us. So I don't know, when will this thing finish? Well, again, we're working backwards. What this is really asking is how long? What's the time it's going to take to infuse this amount? So we're starting at the set flow rate, what's being actually administered to the patient, the 60 drops per minute. So 60 drops per 1 minute. And then again, just like before, we're going to go through the process. We're going to convert our drops into milliliters. 1 milliliter here is 12 drops, or 12 drops per milliliter. That's going to give us now 60 milliliters in 12 minutes, or divided out 5 milliliters per minute. And we can go ahead now and figure out 8,000 milliliters. How long would that take? 5 milliliters per 1 minute. Going into a proportion now because we still want milliliters and we still want minutes. We just want to go from 5 milliliters to 8,000 milliliters. We cross multiply and divide, we are going to get what? What's that? 1,600 minutes. Perfect. And now, of course, 1,600 minutes is going to get converted into hours by dividing by 60. Which comes out to be 26.67. or 26 hours. 0.67, most of you should notice, is 2/3. 2/3 of an hour is 40 minutes. If you left it as 26.67 hours, that'd be fine too. Let's go ahead and take our break. We'll come back and we'll talk about dosages based on weight and body surface area.